Hello, Brian Miller-Hicks here, continuing series on Earth Science and Geology. We're going to focus on clouds and precipitation and what goes into that. It has a lot to do with moisture in the atmosphere, water vapor, pressure, high and low pressure, and cooling and heating of air as it goes up and down. In my background is a painting I did of a rather dramatic lightning storm. Who says that science can't involve art as well? It's a watercolor painting. So we start with moisture and humidity. Moisture, water vapor in the atmosphere is extremely important in driving weather. Humidity, of course, is a percentage of water vapor in a given parcel of air. So let's look at water in and of itself. What is it? Water is H2O. 2 hydrogen atoms, 1 oxygen atom bonded together to make H2O or water. On our planet, in our planet's atmosphere and the surface of our planet, water can exist in 3 phases. It can exist as a solid, or ice. It can exist as liquid water, and it can exist as a gas, as water vapor. When it goes from one phase to the other, heat is either released or absorbed. So let's look at the phase change from solid, from ice. That means the water has to be temperature of at least 32 degrees Fahrenheit or lower, or 0 degrees centigrade or lower. As ice sublimates, and what is sublimation? Sublimation is the conversion of ice to water vapor without going through the liquid phase. It's a direct pathway from ice to water vapor. As it goes from ice to water vapor, heat is absorbed. It takes heat to convert ice into water vapor. If we look at water vapor and we want to convert it back to ice, we want to freeze it. Okay, water vapor exists at a temperature above freezing point. So what do? We release heat. We get rid of the heat that's within the water vapor in that phase and freeze it down to ice. So look at these phase changes. As ice melts, in other words, as it goes from solid to liquid, it absorbs heat. Heat must be applied to ice, must be absorbed by ice to convert from solid to liquid water. Further, if you add more heat to that liquid water, absorb more heat, goes from liquid to water vapor. All this is important in understanding the dynamics of moisture and water movement and water transformation between each phase in driving weather. Let's go the other way. Let's release heat. So we're taking water vapor, we're condensing that water vapor into liquid. As vapor condenses to liquid, as the water vapor droplets coalesce with each other to form bigger droplets, eventually turns into liquid water phase, and heat is released. In other words, the average temperature of water as a liquid is less than the temperature of water as water vapor. If we continue to release heat, we'll freeze water from liquid to solid. Okay, so the cooling of water from vapor to liquid to ice releases heat. The heating of water from ice to liquid to water vapor absorbs heat. That introduces the concept of humidity. Now, to start off, let's know the fact that cooler air cannot hold as much moisture as warmer air. This is a little bit of a complicated graphic, but I'll lead you through it. So let's look at this diagram and note a few things. Let's start with the temperature gauge up here. Temperature is at 25 degrees centigrade, or about 77 degrees Fahrenheit, and it remains constant throughout this graphic. Now, at that temperature, the saturation point of air in this flask is 20 grams of water vapor. That means when there's 20 grams of water vapor in this flask as compared to 1 kilogram of air, that is saturation of that air in the flask. The air can accept no more water vapor. It's saturated. That leads to the concept of relative humidity. We start out at 25 degrees centigrade with 5 grams of water vapor in this flask and some liquid down here. So water vapor content is 5 grams. The maximum amount of water vapor you can get in this 1 kilogram of air at 25 degrees centigrade is 20 grams. So 5 grams divided by 20 will give you the relative humidity of 25%. 25% humidity. In weather forecasts, you'll often hear, well, it's a warm, muggy day today, the temperature is 90 degrees, humidity is 80%. That's a lot of moisture in the air, and warm air can contain a lot of moisture. And if you get a temperature of 90 degrees at 80% humidity, guarantee that's going to feel very hot and very muggy because of the water content in the air itself. As this progresses, note the liquid layer down here. More and more water vapor is going to evaporate from this liquid into the air above it. So progressing to 10 grams of water vapor, now we have 10 grams over the saturation mixing ratio of 20. We have relative humidity of 50%. And then to the next point, if you have 20 grams of water vapor, that's as much as you can get in this air mass. That would be 100% humidity. Okay, let's look at the second case. Now we have temperature as a variable. We start out at 20 degrees centigrade in 1 kilogram of air. So at 20 degrees centigrade, there's 7 grams of water vapor in this flask. The saturation mixing ratio at 20 degrees centigrade is 14 grams. So right away, you know we have a relative humidity of 50%. Let's cool the temperature down to 10 degrees centigrade. The saturation mixing ratio changes. Colder air cannot contain as much moisture, so it contains less moisture at saturation. That means it takes less moisture for a cold air mass to become saturated. That means the colder the air is, the less water vapor it can hold until it starts condensing out. So now the relative humidity is 100% because at this temperature, it can only hold 7 grams of water vapor before it is saturated. Let's decrease the temperature even farther to 0 degrees centigrade or freezing point of water. So saturation mixing ratio is only 3.5. At water vapor content of 3.5 grams, we have 100% humidity. We cannot have 7 grams of water vapor in the air. We can only have 3.5 grams. That extra 3.5 grams will drop out and condense to liquid form at that temperature, and just a little bit below 0 degrees centigrade, of course, that water starts to freeze. So simply put, the lower the temperature, the less water vapor the air can hold. The higher the temperature, the more water vapor the air can hold. So this is an illustration of something that we call dew point. Dew point is a temperature measure. Dew point is the temperature at which water condenses out of the atmosphere, out of the air. So if the air is chilled or cooled below the dew point, it will start to condense. And you see that as a thin film, as a thin film of condensed water droplets on the outside of these glasses of very cold liquid. Dew point can also be stated as the temperature at which the air becomes saturated. So if you go out in the early morning, it's cold, you can see dew on the grass. Dew at temperatures above 0 degrees centigrade can be fog or dew or clouds. Once the temperature drops below freezing, then the dew becomes frost. Here's an important concept when it comes to understanding the concept of cooling and heating of air through rising or sinking parcels and water vapor and so forth. So air rises when it gets heated up. The sun heats the ground. You see that a bubble of air may form above the warm ground because warmer air is less dense, so it tends to rise. That's what we call a rising thermal. Then it reaches an elevation or a height or an altitude above ground surface called the condensation level. And I'll explain that in a little more detail in this next. Now, adiabatic cooling is illustrated here again as it rises, as air rises and cools from 32 to 22 to 12. It cools at what we call the dry adiabatic rate here. Temperature of rising air drops 10 degrees centigrade per 1,000 meters. At this level, called the lifting condensation level, the air is so cool that it can't hold moisture, so moisture starts to drop out, starts to condense into water vapor and then tiny water droplets, and starts to form clouds. Now there's a change in the adiabatic rate. Down here below the LCL, it's the dry adiabatic rate at 10 degrees per 1,000 meters. Above the LCL, the adiabatic rate of cooling slows down to 5 degrees per 1,000 meters. It slows down because as water condenses, it releases heat. Remember when we were talking about that? As water condenses, it releases heat that expels a little more heat into the surrounding air so that it doesn't cool quite as quickly. Here we take advantage of the rising of hot air. We can heat the air within these balloons, and as the air in the balloon is warmer and less dense than the air surrounding it, it starts to rise. If any of you have been to this festival, I have not, but it's on my bucket list. Rain shadow. What is a rain shadow? Well, again, as air rises, it cools. In some situation, air is forced to rise. For example, when an air mass comes in from the ocean that's full of moisture, laden with moisture, it runs in along the coast and then it runs into a mountain range. What happens? Well, the air has no choice but to go upwards. As it goes upwards, it goes through adiabatic cooling till it reaches the late condensation level, and it starts to cool and condense into clouds, and then it drops its moisture. As it drops its moisture, most of the moisture is squeezed out of these clouds on the windward side of the mountain range, and the rest of the air, of course, it has to keep going. It flows over the top of the mountain range and down, and as it does so, it carries much less moisture with it, so this is much drier air. So rising, cooling, wet air releases its moisture through condensation, and it gets over the other side of the mountains. It's drier air, and it sinks into the desert valleys as dry air, and that's what makes or causes what we call a rain shadow desert. Here's an example of rain shadow desert here in California. The Panamint Ranges are very high mountains, I believe up to 11,000 feet above sea level. And Death Valley, of course, is at sea level or lower. So this is a rain shadow desert caused by moisture piling up on the other side of the mountain ranges. So now that we know about lifting condensation level and the formation of clouds, let's look at different types of clouds. Clouds are just collections of water vapor up in the troposphere, in the atmosphere. And there are different types of clouds. Clouds, of course, are formed or made of water drops, water droplets. Often it is a condition of droplet formation that there has to be some kind of seed, some kind of dust particle of a substance around which water vapor can coalesce. So aerosols play an important role here. So the smallest water drops are very small, but then they collide with each other and accumulate into larger and larger drops. Typical raindrop is 2 millimeters, or 0.2 of a centimeter. If you're familiar with the metric scale, a centimeter is about, an inch is about 2.54 centimeters. So this is still small, but it's relatively bigger compared to the tiniest little water vapor particles, or water droplet particles, I should say. Cloud types. We classify clouds according to their altitude and according to their shape or form. So we have low clouds at about 2,000 to 4,000 meters. We have middle clouds from 4,000 to 6,000 meters above the Earth's surface. And we have the forms that are stratus. Stratus are stratified or layered or fairly flat-lying clouds. And we have nimbo, which translates to storm-like. So if you see a cloud name with nimbo in it, that means it's got the potential to rain on you. Okay. So we have cumulus clouds, which are puffy clouds, cirrus clouds, which are high puffy clouds or high layered clouds. So we have different types of clouds. We have nimbostratus, stratocumulus, pure cumulus clouds or fair weather clouds, and clouds that have strong vertical development, meaning rising and falling air currents, are called cumulonimbus if they generate thunderstorms and even tornadoes or the like. So let's look at some photographic examples of these different types of clouds. We have the pure cirrus clouds, which are very high, typically, wispy looking clouds, sometimes called mare's tail clouds, because they kind of look like a white horse's white tail. High altitude clouds, fair weather typically. Cirrocumulus, cumulus is puffy cloud, and they're up at a high elevation as well. Cirrostratus, high clouds that are layered or flat, and they too are kind of wispy and thin, and you can get an effect of a halo as the sun shines through these very high, very cold, icy clouds that forms kind of a halo around the sun, because the sun is transmitting its light through millions of tiny little light prisms, which are ice crystals. Altocumulus, the middle altitude clouds. Cumulus clouds are puffy clouds, so they have that cotton ball shape to them. Altostratus, very high, middle height clouds, hazy clouds, thin clouds, as you can see here. Nimbostratus, these are stormy clouds. Nimbo meaning storm or dark. You can see how dark they can get. The darker the cloud is, the higher the concentration of water vapor is in that cloud. So this is getting set to perhaps rain. Cumulus cloud, again, the puffy cotton ball clouds that people see rabbits and dogs and other animals with in their shapes are called cumulus clouds. Cumulonimbus clouds, so we have nimbus, storm cloud, we have cumulo, puffy clouds. So cumulonimbus are huge, gigantic, puffy, stormy clouds that indicate vertical movement of strong air currents going up and going down in response to air pressure, in response to temperature changes, and in response to moisture circulation. Cumulonimbus definitely will generate storms, including thunder and lightning storms. A thunderstorm can develop as a cloud is in its cumulus stage. It's still puffy. You have rising warm air, these red arrows. As the cloud develops, it develops a circulation where warm air rises, but it rises so high that it starts to cool. It starts to cool, it starts to drop out its moisture, and you get some heavy rain. Then as the moisture is dissipated, you no longer have warm rising air feeding warm moist air into the cloud system. So the cloud itself gets squeezed out of its moisture and gradually dissipates, turns from heavy rain to light rain. Lightning storm, of course. A lightning, as you know, is a discharge between a negative and a positive electrical pole, many times between the earth and the cloud, but just as often from cloud to cloud. Now, lightning, you see, is a phenomenon of light that is caused by high discharge of electricity, sometimes heating up the gas in the atmosphere to temperatures of 50,000 degrees Fahrenheit, very high voltage. So the glowing light you see here is actually gas that's being heated by the electrical currents to very high temperatures and until they reach a glowing stage that you see here. The thunder is generated by the rapid expansion of these gases from these discharges. And the rapid expansion causes huge vibrations to set up big sounds that you experience and hear as thunder. Let's take a closer look at precipitation. Now, precipitation can be rainfall, it can be snowfall, it can be hail, it can be sleet, it can be ice falling to the ground. So there's different types of precipitation. They all stem from the condensation of water vapor, moisture in the air into droplets and drops. In a typical rainstorm, this is the sequence. You have in an equatorial and tropical zone. So in the equator, for example, you get consistent heating of the Earth's surface and the oceans at the equator, so that it's a constant zone of rising, warm, moist air, where moist air converges at the surface and then rises up and feeds and generates and creates thunderstorms, huge cumulonimbus clouds, just a huge production belt of clouds and storms. So in warm clouds, you get saturated air. Remember, warm air can hold a lot of moisture. It rises. As it rises, it cools and condenses, creating droplets of water, which then drop out of the cloud. Okay, you can read this at your leisure. As more condensation is added, the drops grow. Drops are carried higher and higher, they collide and bump into each other, they build up larger drops. Drops get to a large size, they just start dropping down through the cloud from gravity and come out as big water raindrops, like you see here. This is a tropical downpour in some tropical Asian country. Okay, snow. What is snow? Snow is precipitation, but it's precipitation of ice crystals. This is a classic photo of a classic snowflake ice crystal. Beautiful thing, hexagonal in crystal form and habit. Remember, when we were discussing minerals earlier, ice is a mineral. It meets all the criteria of a mineral. It's solid. It's got a structure of organized atoms. It's got a crystal shape. It's natural. So ice is a mineral in that sense. Okay. So a snowfall, the snow that you see on the ground, is composed of untold billions, trillions of these tiny little snowflakes. Beautiful things. Moving on to the next type of precipitation, hail. This is the result or the after effects of a rather powerful hailstorm, I believe somewhere in Texas or Oklahoma, that can actually damage property, including cars. Hail is coalesced ice in roundish pellets that can reach golf ball size, as you've probably heard on weather reports, baseball size. So coming down from the atmosphere, they hit with tremendous force and cause damage. This is not my day at the golf course. I didn't make all these divots, although I'm probably one of the world's worst golfers. These divots were made by hailstones hitting the ground surface. Here is a very, very large hailstone. Notice this is cut in half. It's got concentric rings. The reason it's got concentric rings is hailstones can have a history within a cloud. They can form in the upper reaches of a towering cumulonimbus cloud as an ice crystal, and they can drop. And then they can be swept up in an updraft again and add another layer of ice. Then they'll drop. Then they'll rise up again, add another layer of ice. So they keep adding. The more they go up and down in a cloud, the more layers of ice they can add, and they can get very large with concentric ice rings built around their center. So that's how you get a hailstone of this magnitude. Finally, snow can be dangerous, right? Well, if you get birds in on the act. So with that, we'll close our little talk about precipitation and adiabatic temperature changes and all that.